Assalamualaikum and a very good day. My name is Siti Sofia binti Razali, and today I will be presenting on the topic transmission line and waveguide. In this presentation, we will explore what transmission lines and waveguides are, how they function, their types, key characteristics, and how they are applied in real-life situations. Let's begin. First, let's understand what a transmission line is. Transmission line is a specially designed system of conductors that transmits electrical signals or energy over a distance. These are not just simple wires. They are structured to ensure that signals can travel with minimal distortion and energy loss, especially when the signal frequency becomes high. The basic requirement of a transmission line is two or more conductors arranged in a specific geometry. One conductor carries the signal and the other serves as a return path. Transmission lines are essential for high-frequency communication where traditional wiring is no longer effective due to interference and loss. Now, how do transmission lines actually work? However, there's an important concept here, where is impedance matching. If the transmission line is not properly terminated, or in other words, if the load at the end doesn't match the line's characteristic impedance, part of the signal reflects back. This causes interference, signal loss, or even damage. That's why proper design is necessary. It is to minimize reflection, attenuation, and distortion. Transmission lines have four main electrical characteristics. The first is resistance. This is the natural opposition to current flow in the conductors. Resistance causes heat and signal loss. The second is capacitance. The ability of the line to store energy in the electric field between the conductors. The third is inductance. This represents how the magnetic field around the conductor resists change in current. It stores energy magnetically. And the fourth is conductance. The ability of the insulation between conductors to allow some leakage current. It is the opposite of resistance and ideally should be very low. Together, these parameters determine how a signal behaves as it moves along the line. There are several types of transmission lines, each used for specific application. The first is coaxial line. It consists of a central inner conductor surrounded by a dielectric insulator, then an outer conductor, and finally an insulating jacket. Coaxial cables are widely used in television, internet, and antenna connection. The second is microstrip line. This type has a metallic trace on top of a dielectric substrate with a ground plane below. It is commonly used in printed circuit boards and RF designs. And third is twisted pair cable. This cable has two conductors twisted around each other to cancel out electromagnetic interference. It is used in telephone lines, Ethernet cables, and computer networking. Now, let's move on to waveguides. A waveguide is a structure that guides electromagnetic waves, especially at high frequency, such as microwave or light waves. Unlike transmission lines, waveguides do not use conductors to carry current. Instead, the wave is confined inside a hollow tube and it bounces off the inner wall while traveling forward. Most waveguides are either metal tubes or dielectric field tubes. For instance, optical fibers are a form of dielectric waveguides that guide light. Waveguides are used in radar systems, satellite links, microwave ovens, and optical communication. Next, how waveguides work. When electromagnetic waves enter the waveguide, they reflect off the walls and form specific energy patterns called modes. There are two major types of modes. The first is transverse electric mode, or we call it TE mode. So the function of it, the electric field has no component in the direction of propagation. So the second is the transverse magnetic mode, or we call it TM mode. So the magnetic field has no component in the direction of propagation for the TM mode. These modes help determine how the wave behaves inside the waveguide. However, not all frequency can travel. The wave must be above a certain frequency known as the cut-off frequency, or else it will die out before reaching the destination. So, what exactly is cut-off frequency? It is the minimum frequency that a wave must have to successfully propagate through a waveguide. This value depends on the size and shape of the waveguide. If the frequency is below the cutoff, the wave becomes evanescent, meaning it will decay exponentially and will not carry energy forward. Therefore, only frequencies above the cutoff are useful for waveguide applications, especially in microwave and millimeter wave systems. To summarize the mode of propagation, in TM mode, the magnetic field is perpendicular to the waveguide axis, while in TE mode, the electric field is perpendicular to the waveguide axis. Proper mode selection and waveguide cleanliness are important for ensuring low loss and high efficiency, especially in precision systems like radar or satellite communication. Waveguides come in different shapes and materials, including the first is circular waveguides. It is used when circular symmetry is needed. It converts easily into rectangular waveguides for certain applications. The second is rectangular waveguide. It most commonly used type. Its version like double-digit waveguides improve bandwidth and performance. The last is optical fiber. It is a dielectric waveguide that carries light. It made of a core, cladding, and protective jacket. It used in high-speed internet, medical imaging, and long-distance communication. Here's a quick comparison between transmission lines and waveguides. The first is structure. In transmission line, it uses two or more conductors, while the waveguide is used hollow tube or dielectric. The second is signal type. In transmission line, it has voltage and current, while the waveguide it has electromagnetic wave. The third is frequency range. The transmission line from the low to medium, while the waveguide is high. Next, loss and efficiency. For the transmission line is higher loss, while the waveguide is low loss when clear or dry. For the common uses, in transmission line is used in phones, internet, and TV. For the waveguide, it used in the radar, microwave, and satellites. Both are used in different frequency domains and for different technologies. Let's now look at how this concept appears in the real world. Transmission lines are found in power transmission grids, internet and telephone cables, communication lines across cities and buildings. For the waveguides are used in microwave ovens for cooking, radar system for aircraft and weather tracking, satellite communication for global data links. This plays a crucial role in the infrastructure of modern technology. Why do transmission lines and waveguides matter? Because they are the backbone of modern communication and power systems. From the small wires inside the smartphones to the massive cables under the ocean, and from light-speed data transferred in optical fibers to radar places in the sky. This system allows us to communicate, navigate, and connect globally. They are essential in telecommunication, aerospace, electronics, and even medical technology. To summarize, transmission lines carry electrical signals using physical conductors. They are ideal for low to medium frequency operations. For example, include coaxial cables and twisted pairs. For waveguide, guide electromagnetic waves through hollow or dielectric structures and are used for high-frequency applications like microwave and optical signals. Both are vital for the systems that make our modern digital world function smoothly and reliably.